Our topic is source encoding. What we have learned up till now, we have learned that the information content in a message is equal to the minimum number of digits required to encode the message. Understand it properly. The information contained in a message is equal to the minimum number of digits required to encode the message. Okay, this is we have understood in the last class. And what is entropy? Entropy is the minimum number of digits required to encode per message. Encode per message on an average. Yani on an average, the minimum number of digits required per message to encode is called entropy. This we have seen in our last class. And we also know that HM is what? It is sigma pi I equal to 0 to n, from where we get this is equal to I equal to 0 to n pi log 1 by pi. So make this thing clear. Then we'll go to our source encoding part. What we discussed that day was that this is possible for memoryless source. That is, the messages are not dependent on each other. Each message is independent of other messages. We have learned this. Now let's see if the source is not memoryless, then what? See, let's say we have a sequence like this: M1, M2, M3, so on up to Mn, small n. So these are n messages, n small n messages, number of messages equal to Mn. Let's say we take up to M, we have used small n, so we will take Mn. Okay, this is one sequence of messages. This is one sequence, and we have so many sequences, so that we are actually up to small n number of messages. This is clear. And let's say our mi for in this sequence, for mi it repeats for ki number of times. Clear? There are 0 to n, capital N number of messages in one sequence, and messages are repeating. That is, we are not talking of memoryless channels. So source. So let's say our ith message, it repeats ki number of times. Then we know that from probability theory, limit when n tends to infinity, that is, if this is a large number, then ki by n is actually pi, the probability associated with the ith message. Clear? We have M1 to Mn messages. We are breaking it into several pieces, where one sequence is this Sn, and in this sequence we have 0 to n, capital number of messages. Let's say our ith message repeats ki number of times. Then from the definition of probability, if n tends to infinity, that is, this n is also a very large number, then ki by n is equal to pi, that is the probability of this ith message. That is, this message actually appears for this number of times. I told you this message is appearing for k number of times, m is appearing for k number of times. So from this we can say that m1 is repeating for np1 number of times, m2 is repeating for np2 number of times, this way. And so we can say that probability associated with this sequence is how we take probability. We take probability as p1 associated with the first one to the power np1, because this is repeating for this much number of times. then P2 into NP2 up to Pn NPn. Okay, so this is the probability associated with the sequence n. Now we can say that this sequence is equiprobable. In this to this message, let's say the probability of this sequence, that is PSN, if we take this, then we can say this is equiprobable probable in this setup of data. Okay, so what I am trying to say, that we can say, or we can take this sequence as one message, so that our different messages are equiprobable. Let's say this was for n is 1 lakh, or say 1 million, and this is 1000, this n is 1000. So we can have 1000 such messages which have which are equiprobable, and their probability is PSN. This is what I meant. Okay, so now when these messages are equiprobable, the minimum number of digits required to encode it, let's say, is ln. This will be given as log 1 by p of sn. By definition, in the start I told you, information content is equal to the minimum number of required digits for the message. So to encode this message, we need this thing. Now this is equal to this. So ln can be written as, if we put this into that equation, this comes to pi log 1 by pi. If you put this from 1 to n, so log 1 by psn, if you put this value, I value, this will come to this. But we know that this value, this here to here, is what? It is hm. So instead of this, we can write hm, that is the number of digits required, or that is called the code length. So the number of digits required to encode this message is n into hm, where hm is what? The number of digits required per message. So we can say hm, that is the number of digits on an average required to encode per message. So this will be equal to ln by n. So this is an important result. So hm is ln by n, and this is the minimum value. Though the proof is not given here, but this is the minimum value. That is, below this value, this average number of digits, if this comes to 10, this means you cannot encode this message if you have number of digits less than 10. You can have more than 10, 11, 12, 13, 14, those digits will be redundant. The minimum number of digits required to encode the message will be this hm, that is ln by n. Clear?